Look at an active high-rise construction site. You have ironworkers operating hundreds of feet in the air, balancing on exposed steel beams with nothing but open sky around them. An unfinished building is actively fighting to tear itself apart. Gravity is pulling massive loads downward, wind shear is pushing laterally against the frame, and human momentum shifts unpredictably across narrow surfaces. When you are dealing with multi-ton steel components swinging from crane lines, being careful isn't nearly enough to keep a structure upright or a worker alive. To survive, the industry relies on a legally mandated rulebook, the Occupational Safety and Health Administration Standards. It's a highly engineered matrix of mathematical precision. These rules act as an invisible armor. They are uniquely formulated to neutralize the lethal physical forces threatening a job site long before a single piece of drywall goes up. Let's look at gravity. The absolute first defense against a collapse during construction is establishing erection stability. A 40-foot vertical steel column standing entirely on its own is incredibly vulnerable to tipping over. To stop that, the code mandates a baseline. Every column must be anchored by at least 4 anchor rods. The assembly must resist a 300-pound eccentric gravity load, calculated exactly 18 inches from the outer face of the column. When a crane hoists a horizontal beam into place, the operator cannot simply drop it and move on. The load stays on the hoisting line until the members are secured with at least 2 bolts, drawn wrench tight. And you can't just keep stacking steel indefinitely. The skeleton can never progress more than 8 stories above the uppermost permanently secured floor. Every anchor, bolt, and vertical limit acts as a structural failsafe. They lock the pieces together, ensuring gravity can't trigger a catastrophic chain reaction of falling steel before the building is connected. Gravity isn't the only force at play. Human momentum is a constant threat when workers navigate unprotected edges and open elevator shafts. On a steel frame, a guardrail is a physical arresting system. It is engineered to catch a falling body, providing the brute force resistance needed to stop human momentum. The geometry is strictly mandated. The top rail of a guardrail system must be installed exactly 42 inches high, effectively intercepting a falling adult right at their center of gravity. And it has to hold up under extreme duress. The system must withstand a sudden 200-pound force applied in a downward or outward direction without failing. If we look at this comparison diagram, public building codes require stairs to be wide, often 44 inches, with closed risers for comfort. OSHA allows temporary construction stairs to be much narrower, at 22 inches, and significantly steeper, but slip hazards are tightly controlled. If temporary metal pan stairs are used, they must be filled in with wood or another solid material before the concrete is even poured. Stairs and rails on a worksite ignore public comfort standards to prioritize rapid access. They are designed for brute force arrest, built to stop deadly momentum the moment a worker loses their footing. At 50 feet in the air, a simple trip becomes a fatal fall. This makes friction and sequence of operations incredibly important, especially along the leading edge of decking. Engineers use shear connectors, metal studs projecting from a steel beam into a poured concrete slab, locking them together. If welded too early, they turn the narrow beam into a minefield. Workers must navigate exposed metal studs acting as lethal tripping hazards. So, the regulations dictate a strict sequence. Shear connectors absolutely cannot be attached to the top flange of a beam until after the metal decking, the actual walking surface, has been installed. By dictating exactly when a specific weld can happen, this operational sequencing proves that, when you're 50 feet in the air, controlling friction is just as critical as controlling gravity. A modern construction site is governed by thousands of these hyper-specific data points. A 1/4-inch maximum variance on a stair tread, a 15-foot height threshold for fall protection. The physics we've explored prove that these measurements represent the exact margin between stability and collapse. If a rail sits below 42 inches, or if that 300-pound load limit is ignored, the safety system effectively ceases to exist. These regulations are the literal mathematical parameters of survival on the steel. They represent the boundary where engineering meets human biology. The next time you walk past the chaos of an active site, look closer. Notice the sequence of the bolts, the rugged temporary stairs, the precise height of the perimeter cables. You are looking at an invisible architecture of safety. It is the ultimate counterbalance to the raw physical forces of nature. designed to ensure the people who build